Okay, so on this page, we take a look at some properties of curl and divergence. So the first two theorems here talk a little bit about how the divergence, the curl, and the gradient are related to each other. So for any vector field whose components have continuous second order partial derivatives, so this is needed so that the mixed partials doesn't, so that you can order the mixed partials however you want. So if you first calculate the curl of a vector field and then calculate the divergence of that result, then this is always equal to 0, right? So in this notation, you calculate inside out. So the curl is calculated first and then the divergence. And no matter what the vector field is, as long as the second order partial derivatives are continuous, this is always equal to 0. There's a slight typo here. This should not be fxy. This should be xyz. There should be a z. So for any scalar function, again with continuous second order partial derivatives, so that the mixed partials are all the same. Well, the mixed partials doesn't matter which order you calculate them in. So here, again, you calculate inside out. So inside is the gradient. So if you first calculate the gradient of a function and then calculate the curl of the result, then this is always equal to the 0 vector. So you have this relationship between the gradient, the curl, and the divergence. And then the next theorem here is stating how the curl is related to conservative vector fields in 3 dimensions, right? So if you go back to the first or second section of this chapter, we talked about conservative vector fields for 2-dimensional vector fields, and that calculation involved the partial derivative of q with respect to x and the partial derivative of p with respect to y. And so now, if we involve the curl of a 3-dimensional vector field, we can use that to determine whether a 3-dimensional vector field is conservative or not. So again, as long as the vector field has continuous partial derivatives everywhere. Okay, so that's how we can determine if a 3-dimensional vector field is conservative. To actually find the potential function, the procedure is similar to before, right? So you integrate each of the components with the proper partial integral, right? So integrate p with respect to x, then you integrate q with respect to y, and then you integrate r with respect to z, and all of them are supposed to represent the potential function. However, they're going to have different terms because of the constant terms arising from the partial integral. And so to reconcile the constant terms, you have to compare the terms among the different results and then combine them to get the potential function. And so if you're able to determine whether a 3-dimensional vector field is conservative or not, that will allow you to apply the fundamental theorem of line integrals to curves in 3 dimensions. So we're not going to look at an example, but the procedure will be the same, right? So presented with a 3-dimensional vector field, if you find that it's conservative through this calculation here, then proceed to find the potential function. Then the line integral can be calculated just by calculating the potential function at the 2 endpoints of the curve. So we're not going to take a look at the fundamental theorem of line integrals. However, let's take a look at finding the potential function to a 3-dimensional vector field.